Let's go to table 13.6. Here we have a scenario where a bank is planning to lend 10 million in 90 days from now, and it wants to lend for 180 day, and the underlying rate will be a 180-day LIBOR. However, this bank will be lending at the 180-day LIBOR plus a spread of 150 basis points, that is 1.5%. Now, after the end of 180-day loan period, the principal and interest will be paid. The concern for this bank is that as a lender, it fears that interest rates may fall by the time it lends the loan, that is 90 days later, when it is lending $10 million, the interest rate in the spot market may be low. However, at the same time, the bank is not willing to let the opportunity go if the interest rates are high 90 days later in the spot market. So in a way, the bank is desiring flexibility. If interest rates are high, it wants to benefit from them. But if interest rates are low, as a lender, it wants protection against it. Now, we know that the loan will be given 90 days from now. So the option expiration is in 90 days. That is the time to maturity of the option. And then the option involves protection for a loan of 180 days. So the loan period is 180 days. There is a put option available with an exercise rate of 9% and a price of 5,023. So to achieve the desired objective of the bank, it needs to buy an interest rate put option at a cost of $5,023 that gives it the right to lend at 9% effectively. Now, the cost of the put again here is something to consider. It is assumed that these $5,023 will be borrowed by the bank at 10.5% the spot rate today for 90 days. So 90 days later, when the put option will expire, the bank will have to pay back the loan that it borrowed to buy the put option for 5,023 plus the interest, so the total amount will be 5,155. Now, just for the calculation of the effective rate, we assume that this will be added to the amount lent, which is 10 million. So the effective amount lent will be 10 million plus 5,155. So that will be the total effective amount lent. But remember, this is only for the purposes of calculating the effective rate of the loan. Now, in this table here, we see again we are given a range of LIBOR rates that can be there on day 90 when the put option expires. Now, as we know, the interest rate put option provides protection if interest rate is less than the exercise rate. So we see in all these cases, the put option here has positive payoff. And remember, these payoffs will be paid at the end of the loan period, that is the 270th day of our timeline. And this is calculated based on 180-day loan period. So we see that the lower is the interest rate, the higher is the payoff on the interest rate put, and it means that the lower will be the amount of interest that the lender will earn in the spot market from lending 10 million at the spot rate plus the 1.5% or 150 basis point spread. So if we take the first rate here, 5% for example, in this case, the put interest rate put is in the money because the put gives the bank the right to lend at 9%, and the LIBOR on day 90 is 5%. Hence, it's more valuable to lend at 9% than to lend at the spot rate of 5%. So the put option is in the money, and the payoff is 9% minus 5% multiplied into 180 divided by 360 and then multiplied into the notional principal, so that is 200,000. That is 10 million multiplied into 9% minus 5% into 180 divided by 360. So that gives you $200,000 as the bank's payoff from the put. And then the amount received on the loan given on day 90 for 180 days, it will be received on the 270th day from now. So this can be estimated as the interest of 325,000 can be estimated as 10 million multiplied into, the interest rate is 5%, but there is also a spread of 1.5% into 180 divided by 360. So this gives us the interest on the loan of 325,000. So on the 270th day, when the loan period will be over, the lender will receive the principal of 10 million plus the interest 325,000. So if we look at this, effectively the lender has been affected adversely by the fall in interest rate on day 90. However, on the expiration of the put on day 90, there is a 200,000 payoff to be paid to the lender on the 270th day because interest rate options payoff are deferred. So we see that the total amount received by the lender will be the amount received from the spot loan plus the amount received from the payoff on the put option. So that is 10.525 million. So the effective rate here can be calculated using the amount we have here, like 10.525 million. That is what the lender will receive in total at the end of the period, and the effective loan was 10.00. Let me just get rid of this line, and okay. So this was 10.005155 raised to the power 365 divided by 180 minus 1. So that should be approximately equal to 10.82%. Similar calculations can be done again for the other rates. Now, this is a put option, so we see whenever the interest rates are low, there is a positive payoff from the put option, and that supplements the lower interest payments on the actual loan, resulting in no case the lender receiving less than 10.82%. So we see that when interest rate falls in future, the lender is protected in all the cases. However, if interest rate rise, the lenders participate in that and earn a higher interest rate. Now we can compare the effective rate on the loan against the effective rate without the put here. So if there was no put, then we see that there is a lot of variation possible in the payoff from the loan, and the lender in this case is exposed to the risk from falling interest rates, and it can be as low as 6.7%. Now these are again shown as in figure 13.4, and we see that here the lender has a floor. This is the 10.82% return on the loan. In no case effectively the lender is earning less than 10.82% thanks to the interest rate put. The payoff here when the interest rates are rising is slightly less than the uh, interest rate earned by not having any protection. However, this is explained by the cost of the interest rate put that was purchased to protect against the downside here. Okay, next we are doing interest rate caps, floors, and collars. So far, we assume that the borrower or lender will borrow or lend in future at a given day and will pay or receive a single payment of interest at expiration of the loan period, when they will also be receiving the principal amount or paying the principal amount. However, if future borrowing and lending is at a floating rate with more than one period of payment or receipt of interest, we will need a combination of interest rate calls or interest rate puts to hedge the risk in borrowing or lending. The combination of interest rate calls used to protect a borrower from the risk of rising interest rates on a multi-period floating rate loan is called interest rate cap. Interest rate cap contains a series of interest rate calls, and each call is called a caplet. Similarly, the combination of interest rate puts used to protect a lender from the risk of falling interest rates on a multi-period floating rate loan is called interest rate floor. Each interest rate floor contains a series of interest rate puts. Each put is called a floorlet. A collar is a combination of a long cap and a short floor at different exercise prices. This is generally done to reduce the cost of a long cap. An interest rate cap has caplets or interest rate calls which are independent from each other. In table 13.7 we have an example that illustrates the use of interest rate cap. So here we have a scenario. On January 2, a company is taking out a loan of 25 million for a 1 year period where interest is paid quarterly and the rate is LIBOR. Now the company needs protection against a rising interest rate because it's a pair of the LIBOR. So if interest rate rise, that means LIBOR will rise and hence borrowing will become expensive. Now, to protect against this risk, there is an interest rate cap available with an exercise rate of 10% for a premium of $70,000. Now, on January 2, the LIBOR in the spot market is 10%, which means that we already know the payment to be made for the first quarter on the 2nd of April, the rate that will be used will be 10%, and it's already known today. The cap is purchased for 70,000, and it is assumed here that the 70,000 paid for purchasing the interest rate cap is coming from the loan proceeds of 25 million. So that is why we see here the net cash flow from the loan being reduced by 70,000. And alternatively, if there is no interest rate cap, then the net cash flow remains the same value of loan, 25 million. Now, 90 days later, on April 2, the LIBOR is 9.75%. So interest rates have gone down. So the first caplet is not in the money. It will be expiring out of the money because the market LIBOR is 9.75% and the exercise rate we have is 10%. So therefore the caplet payment will be none. However, we already know how much we will be paying in interest for the first quarter because at the start of the loan period interest rate was 10%. So the interest due on the loan on 2nd of April for the first quarter is 10% multiplied into 25 million multiplied into 90 days divided by 360. Remember, we will be using the exact day convention, so we will have to count the number of days here. So this will be paid. So now this is a negative cash flow, and there is a reason why we are putting these signs here with the cash flow. So we received the cash flow of 25 million, but we paid the cap payment of 70,000, so we have a positive cash flow here. But all the remaining cash flows are negative, which means that we are paying back interest and then principal also. Now, on July 2, which is the end of the second quarter, and the total number of days from April 2 to July 2 are 91. And the interest rate, that is LIBOR, in the spot market on July 2 is 12.375. That means that the cap is in the money. The second caplet here is in the money. Why? Because we have the right to borrow at 10% for this quarter and the next quarter, which is the quarter ending October 2. So we have the right to borrow at 10%, and the market rate is 12.375% for the next quarter. So this caplet is in the money, and the payoff for that needs to be calculated. However, as we know that the payoff for the interest rate option takes place at the end of the loan period. So whatever the payoff is from the caplet, it will be paid at the end of the quarter, which is October 2. So that is why we see a 0 here, but the gain on this second caplet is calculated and is received at the end of the third quarter. Now, the interest payment due on the 25 million loan will be based on the interest rate at the end of the first quarter, which is April 2, 9.75% multiplied into 25 million multiplied into exact number of days, that is 91. So divided by 360, so that gives us 616,146, and this is just because of the 1 day difference between this quarter and this quarter. So we see again a negative interest payment of 616,146 here. We paid the first quarter interest, we paid the second quarter interest. There is a gain in the second quarter on the second caplet, but this will be received at the end of the third quarter, and that is why this cash flow is shown here on the timeline to be received at the end of the third quarter. Now, at the end of the third quarter, the interest rate is 11.5, which again is higher than the cap exercise rate of 10%, which means the caplet here, that is the third caplet, is in the money. So the payoff again will be calculated here, but it will be received at the end of the fourth quarter. So we will calculate this as 11.5% minus 10% multiplied into 25 million, and then 90 divided by 360, so that is 95,833, and that is why it is shown here. The interest payment for the third quarter will be based on the interest rate at the beginning of the third quarter, or that at the end of the second quarter, which is 12.375%. So 12.375% multiplied into 25 million multiplied into 90 divided by 360 gives us 790,625. So we see that the net cash flow here is 638,889. This is because this is the payment that needs to be made, but this is reduced by the amount of the gain on the interest rate cap. The same is the case with the fourth quarter payment, where we make an interest payment of 734,722 based on the interest rate prevailing at the beginning of the fourth quarter, or in other words at the end of the third quarter, multiplied into 25 million into 90 divided by 360, and then adjusting it with the gain on the third interest rate cap. Now, the net cash flow here can be put into an Excel sheet to get the effective rate of the borrowing with an interest rate cap. In our case, it is 10.78%. This can be compared against the IRR, or the effective rate of the borrowing without the interest rate cap, which is 11.5%. So here we see that the use of interest rate cap has effectively reduced the borrowing cost compared to a position that is not hedged. Next, we explore interest rate floor, and this is used by lenders, as we discussed in the previous slides, to hedge the risk of a multi-period lending position. We have a scenario in table 13.8. Let's have a look at it, and it's just the opposite of what we observed for an interest rate cap here, because it's an interest rate floor. So if the LIBOR is less than the exercise rate in the interest rate floor, which is 8% here, the floorlet will be in the money, and there will be a positive payoff. Otherwise, it will not be. As in the case of borrowing, the first interest rate is known, and the quarterly interest for the first quarter will be calculated using the LIBOR on 16th December, which is 7.875% here, and that means that the lender will receive this much in interest on the March 16th for the first quarter of the loan. In the second quarter, we see that interest rate is high, more than 8%, and that is why this floorlet, the first floorlet, is out of the money. That is applicable to the second quarter. At the beginning of the third quarter, the LIBOR is 7.125%, and this implies that the second floorlet, which is for the third quarter, is in the money, as the exercise rate is 8% and the LIBOR on the 16th of June is 7.125%. However, the payoff, as we know, will be received at the end of the third quarter, that is here. So the payoff will be 8% minus 7.125% multiplied into actual day, that is 91, divided by 360 multiplied by 15 million, and that is 33,177. So here we are using the actual day 91 for the third quarter to estimate the payoff from the second floorlet. At the beginning of the fourth quarter, that is on 15 September, again the interest rates are lower than 8%, 6% to be exact, and we see that the third floorlet is also in the money. So the payoff will be calculated as 8 minus 6% multiplied into 92 divided by 360 multiplied into 15 million, and hence the gain is 76,667. So whenever the interest rates go down, the floorlet are in the money, and when the interest rates are higher than the exercise rate, the floorlet is out of money. The cash flows are again here because it's a lending position, so you can see that the effective lending amount is 15 million plus the cost of the interest rate floor, and then we assume that the lender is receiving quarterly interest adjusted for any payoffs, and then finally the principal payment is also received along the interest and the payoff from the floor. So we see here that the effective lending rate for the lender with the interest rate floor is 8.17%, and again this can be easily done in an Excel sheet by estimating the IRR of these cash flows. The same can be done for the situation in which the lender is not hedged using interest rate floors, and we see that in that case the effective lending rate is 7.41%, which is lower than the one with the hedged position. So finally, here we have interest rate collars, and as we know that interest rate collars involve a combination of a long position in interest rate cap and a short position in an interest rate flow. This is a useful strategy for a borrower to reduce the cost of buying a long cap. When the borrower goes short the floor, the premium received from selling the interest rate floor offsets some of the cost of buying the long interest rate cap. It may be possible in some cases to have a zero cost collar where the premium received from selling the floor is exactly equal to the premium paid for the long cap. This will require the floor to have an exercise rate such that the premium on the floor exactly equals the premium on the cap. By selling the floor, the borrower is giving up gains from falling interest rates below the floor exercise rate. Remember, the borrower here is worried about rising interest rates, so he is buying a long cap, but that may be expensive. Now, to cover the cost of the hedging strategy, he enters into an interest rate floor as a seller, and the premium he receives from there is used to cover some or all the cost of the hedging. However, he is foregoing the uh, potential gains from falling interest rates if interest rate fall. Let's look at the example in table 13.9. Here we have a scenario. On March 15, a company is considering to take out a 50 million 2-year loan with interest to be paid quarterly at LIBOR. Now, to protect against rising interest rate, the company is buying interest rate cap that has an exercise rate of 10% for a premium of $250,000. Now, the cost of hedging in this case are too high, $250,000. To offset some of the cost, the company is selling interest rate floor with an exercise rate of 8.5% for $250,000. The interest payments on the loan and the payoffs of the cap and floors are based on the exact number of days and a 360-day year. And this is an illustration. So we see here from the table that on 15th March the LIBOR is 10.5%. So the first payment on the loan is known in advance and it cannot be hedged, as we saw in the case of the interest rate cap and interest rate floor. So the interest rate cap has 7 caplets, 1, 2, 3, 4, 5, 6, 7. And in the same way, the interest rate floor has 7 floorlets because out of the 8 quarterly payments, the first one is already decided. So there are 7 left. So the first interest payment on the loan, that is $50 million, is already decided on the start date of the loan, that is 15th March. Now, on June 15, 92 days, that is the first quarter, has 92 days in it. The LIBOR is 11.5%. So we have to compare this against the exercise rate in the interest rate cap, which is 10%, and the exercise rate in the interest rate floor to see whether any caplet or floorlet that correspond to this first quarter are in the money or not. So given the exercise rate of 10% for the caplet, it appears to be in the money. However, as we did for the interest rate caps and floors, the payoff from this caplet will be received at the end of the second quarter, and that is here. So it will be 11.5% minus 10% multiplied into 92 divided by 360 and multiplied into the notional value, that is here equal to 50 million. So that is 189,583. Then the interest on the loan for the first quarter will be estimated or calculated as 10.5% the LIBOR at the start of the loan, that is March 15, multiplied into 92 divided by 360 multiplied into the loan amount, that is 50 million. So it is 1.341667 million, and this is the net cash flow with the collar. We've also here a column where the net cash flow with cap only and the net cash flow without the cap or the flow has also been estimated. At the end of the second quarter, the interest rate again is high, 11.75%, and again the second caplet is in the money, and we see the payoff is estimated and will be received at the end of the third quarter. Now the next two quarters are special cases in the sense that the LIBOR on the on these days is between 10% and 8.5%, and whenever in the case of an interest rate collar, the LIBOR is between the exercise rates for the interest rate cap and the interest rate flow, that is 10% and 8.5%, neither the caplet or the floorlet will be in the money, and that is exactly what is happening here. So there are no payoffs, neither the floorlet nor the caplet is in the money. Then we see in the next three cases the interest rate floorlet is in the money for respective quarters. In the first case here, it's 7.625%, so less than the exercise rate of 8.5. Again, the seventh quarter and the eighth quarter, we see that the sixth cap floorlet and the seventh floorlet are in the money, as both are less than 8.5%. The payoffs are calculated and paid at the end of the respective quarters. Now, because we have a short position in the floorlet, so these are negative. So given this, if we estimate the IRR of the cash flows in these three columns, we see that with the cap only arrangement, the borrowing will cost 9.93%. With a collar, the hedging arrangement will result in an effective borrowing cost of 9.83%, and without a collar or a cap, it will cost 10.10%. Here we are comparing interest rate options, FRAs, and swaps. A swap can be replicated by using off-market FRAs. We know that to replicate the swap, a series of off-market FRAs must be used, matching the payments or cash flows of the swap over its life. With off-market FRAs, the forward rates used in each FRA contract vary from those implied by fair market valuation. This arrangement of off-market forward rates allow to match the payoffs from swap over time. Now, if we compare a swap to an interest rate option, on settlement, the payoff from a long call is zero if the LIBOR on the expiration is equal to or less than the exercise rate, and it is LIBOR minus the exercise rate if the LIBOR is greater than the exercise rate at expiration. The same payoff is received by shorting a put, where if LIBOR is less than or equal to the exercise rate at expiration, the received payoff is minus x plus LIBOR, because minus into minus is plus and minus into plus is minus. So this will become plus LIBOR and minus x, which is the same as this one. In case LIBOR is greater than the exercise rate at expiration, the short put will have a zero payoff. So combining a long call with a short put on interest rate will give us a payoff of LIBOR minus the exercise rate. If we replace and select the exercise rate such that it is equal to the swap fixed rate R, it will become LIBOR minus the swap rate. Hence, combining a long interest rate call and a short interest rate put positions into one will enable to replicate the payoff on a swap.